Okay, so let's get started with the flow matching. Okay, so last time we discussed some fundamental things about the flow matching, which is the another type of the judgment model. We especially saw some kind of the details, the math in terms of how we can derive some kind of the exact loss function for the training. And we're gonna get into more about some kind of the higher level the ideas about like how exactly this works and how we also need to implement this and how we can compare this with the diffusion models that we discussed so far. So let me briefly remind things that we discussed last time. So last time we discussed some kind of things about the normalized flow and the concept of the push-forward operator. So now what we are going to do in terms like designing some kind of the generic model is that we are going to basically introduce the mapping function, the pi here, which is basically mapping some kind of a given the base distribution, which is typically the standard, the normal distribution, through the into some kind of the data distribution that we want to basically learn through some kind of the training. So when you basically see that this pi is kind of the function, which is the mapping the P0, the base distribution, the probability distribution into the data distribution, the P1, the sampling through the P1 distribution can be basically seen as kind of the procedure that we first sample from the P0 distribution, which is the base distribution, and then mapping this into the one of the sample of the P1 distribution. And we basically introduced the term, which is the push-forward operation, which basically means that we are pushing the P0 distribution into the P1 distribution by some kind of given the mapping function pi here. And this kind of the mapping could be basically expressed with this kind of the formulations, right? So this was the basic idea of the push-forward operator. So basically, in terms like making a generic model, what we want to do is basically how we can find the push-forward operator, the pi, mapping the standard number into the data distribution without knowing some analytic form of the data distribution, but taking some of the samples of the data distribution. So for that, basically, we also discussed some kind of the other concepts, which is the velocity field, the vector field, and also the probability path. So given a kind of the mapping function pi here, which is typically called the flow map, we are basically define some kind of the velocity field, which is just like the derivative of that kind of mapping function with respect to time t here. So basically, the mapping function, the flow map here, can be also expressed in terms of the velocity field, which is also giving some kind of the notion of the probability path in terms of how the probability distribution is basically evolving over time through the vector field. So basically, the probability path over the time space, the pt there, has this kind of the relationship between the vector field there, and this relationship is basically represented with the Fokker-Planck equation as shown here. So by solving this equation, we can basically find some kind of corresponding the vector field from the given the probability path, and we can do the other way around. So we basically think this kind of a relationship between these two. So the goal of the flow matching is that when we basically know some kind of the flow mapping the P0 distribution, the base distribution to the P1 distribution, the data distribution, how we can basically learn some kind of a neural net that can capture this kind of the velocity information over time, so in the space. The thing is that obviously if we already know this like the vector field, we say that they show some kind of a mapping, then we don't need to train the neural network, right? So that's kind of thing. So without having the kind of the vector field, the information, how we can train the neural net that can basically learn this kind of mapping is the problem that we are going to solve in the flow matching. So for that, basically what we have seen last time is that instead of like considering the vector field, because like we don't have the information about the mapping, right? So instead of like using considering the vector field, now we are going to consider the conditional vector field, conditioned by the data sample, the x1. So last time we changed the notation, so which means that the x1 here is basically one of the samples from the data distribution, right? So conditioned by the one of the sample of the x1 here, we are thinking of some kind of the conditional vector field. And the good thing is that once we start to consider this kind of the conditional vector field, now we can see that the loss function the regression that we have seen in the previous slide can be converted into this form. Basically, almost the same form of the loss function. We are only changing some kind of the sampling part there, like some kind of the some values for the expectation, right? And so for that, so here the question might be is that, so then what sort of the conditional vector field that should we consider? Actually, there are lots of the options. So it's matter of like, what sort of the conditional vector field that we choose. And the specific the form of the vector field, the conditional vector field that we discussed last time, or basically was this. We chose basically derived by the definition of the conditionality probability test there. So now we are basically considering the conditional probability test, which is defined as kind of the some Gaussian distribution with a some kind of the function of the mean and also the function of the variance. And given the definitions of the probability test, now we can basically derive the flow map here. And by just taking the derivative of the flow map, we can also find the vector field as well, right? So we are basically thinking of like this specific form of the probability test and also the flow map and also the vector field, right? And also there are lots of the options in terms of like what sort of the mean of function and the variance function that you're going to choose. And also the simplest form for the mean function and the variance function was like these two. So by setting like the mean function and the variance function into this form, we could also derive the probability test and the flow map and the vector field corresponding to these definitions, right? So can you quickly like write down like what are some kind of the probability path and the flow map and the vector field for the definition of like these specific mean function and the variance function? 11 get this result. You can check whether your answer is correct. Same with this. Where? Anyone? Yeah, should be fixed. Yeah. So yeah, basically by defining the mean and the variance in that way, in the conditional the probability test, now we can derive the flow map into this form and also the vector field into this form. I mean, so the vector field is basically nothing but taking the derivative of the flow map, right? But this is kind of the most interesting part in the flow matching. The thing is that actually we were defining this sigma mean as kind of the very small number, right? In terms of that, the conditionally probability test becomes something that is very close to the Dirac delta function that is having the peak at the x1, right? So actually, what we can see from all these definitions of the flow map and the vector field is that if we say that actually the sigma mean is close to zero, and if we just like treat them as kind of zero, that what we can see is that the final form of the flow map and the vector field becomes like this. So which means that after like all the kind of the long derivation, what we are getting as kind of the flow map is basically nothing but like linearly interpolating these 2 points, the xt and the x1, right? Basically the simplistic form. So from this, actually what we can see in terms of how we train the flow-based model is that, so this was basically the loss function that we have seen, right? So the difference between the this loss function and also the loss function that we have used to train the noise prediction network for the diffusion models is that for the noise prediction network, we only sample the x1, right? The data point. And then we are perturbing this data point, adding some kind of noise, and then sending this to some kind of xt in this context, and then predicting the noise, and then basically see whether the predicted noise basically matches some kind of the noise that we added, right? So we are only sampling the x1 and basically sampling the xt based on the x1. So here the one difference is that now we are sampling both the x1 and the x0. X1 is basically one of the data points, and X0 will be one of the sample from the standard the Gaussian distribution. And based on that, we are computing the XT here, based on the flow map function here. And our the flow map function was the simplest form, basically simply linear interpolation. So once we basically sample the x1 and the x0, we are calculating the xt by linearly interpolating those 2 points with some kind of the time t. The time is also like randomly sampled, right? And based on that, then now we can also compute the vector, the velocity at the xt. What's the velocity at the xt, given the x1 here? And we can also see that the velocity at the xt with respect to the x1 just becomes some kind of the velocity, which is also for the interpolation between these 2 points for the x1 and the x0. So if we take the vector from the x0 to the x1, that becomes the velocity that we are going to match. And what we are also going to do is that we simply train a neural network that can basically match this velocity by just predicting the value, right? So you can say that actually it turns out that after doing all this kind of the complicated kind of the math, if we define the conditional probability path in this way, then all the process, like training the flow matching, becomes this simple form. Basically nothing but every time we are sampling the time t and also the data point x1 and also one of the samples from the standard the Gaussian distribution. And based on that, we are taking the vector, which is like the vector from the x0 to the x1, and then basically predicting this vector using our neural network. So now you can see that the implementation will be very simple, right? So this is also kind of like all the interesting the things in terms of like, after all the derivation, that you can see that training kind of the flow-based model is actually very simple. And now also you can see that why we defined the conditional probability path in that way, in some kind of through some reverse engineering. So we wanted to actually have this kind of the simplest form, just taking 2 points and just taking the vector from the like one point to the other as kind of the velocity and just like matching this thing. And to basically train out the flow matching into the simplest form, we define the conditional probability path in that way, in a way that we can also have some specific form of the flow map and also the vector field into that equations. So you can think about like the reverse way to achieve this kind of the simplest form in the loss function. What sort of the conditional probability path that we need to basically define. So maybe from this, you can check out these slides again and see like why we define these things in that way. So this is kind of the thing. I mean, while we have seen lots of kind of some complicated some kind of the math underlying the kind of the formulation, it turns out that we can actually train a flow matching the model using this kind of the simplest form of the loss function. Just like taking the samples of not only the x1 and also the x0 and taking the vector from the one point to the other, to the x0 to the x1 is kind of the vector that we want to match, and then basically training a kind of the neural network that can predict this vector. So very simple, the objective function. But now you can see that the meaning of like having this loss function is actually just like learning those vectors, learning the conditional vector field conditioned by the x1. And then that also is having some kind of the equivalence with the loss function that we wanted to actually use. Any questions on this? And you can also see that actually this looks kind of similar with diffusion model in terms of that we somehow sample the xt, and then basically getting some kind of quantity at the xt and train a neural network in a way to predict that specific quantity, right? But the way that we are sampling the xt in the diffusion model was only using the x1 and basically adding some kind of the noise, some perturbation. And also we are predicting the amount of the noise that we added from the x1. And here the thing is that we are not only having the x1, but having some kind of the x0 as well, having some kind of the coupling of these two. And based on that, we are defining some kind of the vector from the x0 to the x1 and trying to basically match this kind of the vector. So kind of the quantity that we are going to predict is different with diffusion models. Clear? Any questions on this? So yeah, I hope you got some kind of the basic idea like how the flow matching exactly works. Then the question might be is that, so why do we care about the flow matching, right? If the diffusion model basically works well, then should we really know about the flow matching? So there might be some kind of question. And also, does flow matching the basic model work better than the diffusion models? So these are some kind of some natural questions, right? So actually, also this is the very interesting point. That is very recent kind of some observation that people are basically seeing in some kind of very recent research. The thing is that while the flow matching the model is kind of working, obviously the output may not be very good. I mean, so there are still some kind of the things that we can improve in terms of the output of the flow of the model. But the very interesting point, the first interesting point for the flow-based model is that the output tends to learn some kind of the more some sort of the straight the trajectories, which is basically avoid some kind of the crossing each other. So when you think about that, these are some kind of the some base and the target distribution, and the purple color is some kind of the base distribution, and the red color is some kind of the data distribution. If you just randomly sample the 2 points, x0 and the x1, and do some kind of linear interpolation, then we're gonna see that there can be lots of some kind of the trajectories that can cross each other. But without introducing the proof here, actually what we can see is the output of training the flow matching the model is that once we basically train on the flow matching the model, then we can typically see this kind of output, which is basically avoiding some kind of the crossing of the trajectory, which is basically having those kind of the outputs. And given this, actually what we can do is that once we basically have some kind of some pre-trained some kind of the flow-based model. So let's say that Z1 is basically some kind of the trained flow-based model. Then what we can do is that we train again. We just train the flow-based model again using another neural network, or where we can also consider like just fine-tuning the pre-trained network. But not just like randomly sampling the x0 and the x1, but now sampling those pairs from the pre-trained model. Make sense? So previously, basically what we have done is that we are independently sampling the x0 and the x1. Just randomly making any kind of some kind of pairs of the x0 and the x1. But instead of that, now we can consider basically sampling the x0 and running the generative process of the flow matching, basically solving the ODE, right? And then we can get the x1. So now the pairs of the x0 and the x1 basically comes from the pre-trained the flow-based model. So we are basically using some kind of the training the flow-based model once, and using that information to train again another kind of flow-based model. So this is typically some technique which is called the reflow. But if we basically train the flow matching model again, what we get is that, so this is basically the output of the first the flow-based model. Basically, you can see that it tries to basically avoid some kind of the crossing, making some kind of the trajectories like this. So now we are basically sampling the x0 and the x1 based on this model, and basically train again another flow-based model. Then we get this. So interestingly, now you can see that it tends to make some like sector trajectories like this. And we can also repeat this again. Basically now taking the second model as some kind of the some base for the sampling and training again. Then we get more straight trajectories like this, even straighter trajectories. And actually, what we can see is that as we have some kind of the more like the straighter trajectories, it becomes like much easier to solve the ODE, right? Because like once you basically get the velocity from the very beginning point, you can just like go straight without basically sampling like more and more, right? So basically having the more like straighter the trajectories basically help to basically run the generative process with some fewer steps, with some kind of the more accurate outputs. So this is kind of like very interesting kind of findings in terms of that what we need to do in terms like reducing the number of the steps in the inference in the generation time is to basically train the flow-based models multiple times. You basically train the flow-based model like once, and using that train another flow-based models and just repeating more times. And why do you get like this straight-line trajectories as you basically train the multiple times? So actually, if you see the loss function again, actually this loss function itself is basically measuring the straightness of the trajectories. So basically, we are sampling the xt in the middle of the x0 and the x1, and try to see whether the vector that we are predicting at the xt is basically heading the direction from the x0 to the x1, right? Which means that actually this loss function itself is basically measuring how straight all the trajectories are. So since we are basically minimizing this loss function like the more and the more and the more, as we basically repeat like the multiple times, we can see that actually the trajectories get straighter. So there are lots of the theory underlying this. I just keep some of the theories there, but this is kind of the some of the outputs that we can see. So this is like very interesting, the result. And here, like one more interesting is that now we can apply this idea not only for the flow matching the model, but actually for any generative model, for any pre-trained generative model, we can consider applying this kind of same technique. But before we get into that, actually, let's see some kind of the results here. So these are the some kind of results when we repeat, like train the flow-based models like multiple times. So one rectified flow means that the output, the flow-based model. The two rectified flow is the next time, the training. And three rectified will be the next one. So you can see that if you see the FID, at the very beginning, the FID is like very high, like 300 something. It's very high number, right? But if you basically train another flow-based model, it goes down to 12, which is like way smaller. And if you train one more time, then it goes down to 8. So we can see that like by repeating this kind of the training of the flow-based model, we can see some kind of the improvement of all the results. And especially like the number of the 8, for something of the FID is very small. When you think about that, actually the number of the evaluation is basically one step. So what's the meaning of like having the one step, the ODE solver? Like solving the ODE with just like a single step. That basically means that we are not actually solving the ODE with some kind of the solver. We just like take the velocity vector at the very beginning and just like go straight with some kind of the time that we have, right? Just getting some kind of the velocity information at the beginning point from the sample of the standard Gaussian distribution, and then just like go straight. That becomes the final outcome, right? Even for this kind of the one step kind of generation, we are achieving some very accurate output, very good quality of the outputs of the generative process, which is like very interesting results compared with that diffusion model typically requires like tens of some kind of iterations to get some kind of good results. And the reason why we can get some kind of good result with some like single step degeneration is that the trajectories are basically straight. So we can basically do some kind of the one step degeneration by just directly taking the velocity information from the very beginning. So this is like very interesting, the output. And as I mentioned before, like the more interesting might be is that actually we can apply the same idea for the stable diffusion as well. For any generative models, because like the goal of the generative model is the sampling the x1 by starting from the x0, right? So for any like GAN, for anything, what we do is that we first sample from the unique Gaussian distribution and then do some kind of the mapping process, whether it's kind of the generator for the GAN or some kind of the denoising process for the diffusion models. So we are going to basically have some kind of the pairs of the x0 and the x1, right? From any kind of the pre-trained generative models. So actually what we can do is that from the stable diffusion, from the pre-trained stable diffusion, we can sample lots of the pairs of the x0 and the x1 using some pre-trained stable diffusion. And then using these pairs to train a flow-based model. Just like doing the same thing, but not taking pre-trained flow-based model as kind of some base model, but using any kind of diffusion model or any generative model. So we can really consider like taking the x0 and the x1 pairs from the stable diffusion and using these to train a flow-based model. Then what we can do is that obviously we cannot achieve some better quality than the stable diffusion because now we are using the output of the stable diffusion for the training data, right? So there is no expectation that we're going to get some kind of the even higher quality. But the thing is that we can make the trajectory straighter, which means that we can run the generation the process with some way fewer steps. So those are some kind of the results in terms of that we are reducing the computation time in terms of like reducing the number of the steps. So we don't need to basically run the denoising process like multiple times. We can just solve the ODE with some kind of very few steps, while still basically achieving some kind of good quality. So this is kind of the idea in terms of that how we can make the generation the process be faster in the generative model. So if we see some kind of the literature of the generative models in recent like some years, okay, let me finish this. So like for the GAN and the VAE, we've seen that actually the quality is not very good, but still the speed is like quite fast, right? So the idea in terms of like improving the quality while sacrificing the speed was basically having some multiple steps of the denoising, right? So that's why basically we could get some kind of good quality by refining the X0 of the prediction in the diffusion models through the multiple the denoising process. And we could also basically reduce the number of steps by converting the DDPM into the DDIM, right? When you have some kind of deterministic sampling, which is kind of also equivalent to solving the ODE, right? Then we could also reduce the number of steps while getting some kind of the good quality of the outputs. And the idea in terms of reducing the number of the steps further, while also achieving some kind of good quality, is to basically distill some kind of the information from the pre-trained the diffusion models, and then just like training another the rule-based models in a way that we can get some kind of the stricter the trajectories. So this is basically what we are seeing in the recent the days.
Yeah, so I was curious. So in theory, we can train some diffusion model. Then if it performs well, we can train the flow model and then just use that flow model in production because it would be much faster.
Yeah, that's exactly what people are doing. So once you have some kind of really good quality of the diffusion model, but they might require like running these steps like multiple times, we can just like make another kind of clone like this, but like compromising the quality a little bit. You basically won't be able to get kind of the same quality, like sacrificing the quality a little bit, but basically we can make it way faster. Basically like it by making this the trajectory straighter. It basically somehow like branching out from some kind of trained some diffusion model. It's just making another some kind of the flow-based model, which is running way faster. So this is the technique that people are really using to make the generation the process the faster. So this was kind of really important factor in terms of applying those kind of the techniques in the many applications in the real some industry the problems, because like if it takes like seconds to just generate like single image, then would it be really useful for many applications? Because all users will need to basically wait for that like the several seconds or something even longer than that to get some kind of the single image, right? Also, it is like involving lots of the computation. Like all the GPU computation is kind of the cost, right? So that also basically makes some kind of burden in terms of utilizing the diffusion models. But by converting the diffusion model into the full matching model, we can basically make the generation way faster. So even with some less than 1 second, we can get some kind of good result while also reducing the computation time and also the computation resource more. So this is kind of the very recent the idea in terms of how we can make the generation faster by just like retraining some kind of flow-based model. But then what would be some kind of the some downside in terms of like reducing the number of iterations? Any kind of ideas?
We need to prepare the data sets and that requires sampling of stable fields, so it will take a lot of time.
Yeah, so that's also kind of like one big thing. So for training another the flow-based model, typically for the training the flow-based model using the stable diffusion, people typically use like 1 million samples of the X0 and the X1, which means that you also take some kind of the computation time for that, plus some kind of the time for training the flow-based model. So that's was kind of like one big thing. So if we can, even without like using some kind of the pre-training model, if we can also get some kind of good sample of the X0 and the X1, just to train the flow-based model from scratch without having some kind of the existing different model, that will be way better. So that's really some kind of the research problem, I think. But in terms of like applying those techniques for some kind of the applications, do you also see some kind of the downside in terms of like reducing the number of the steps? I mean, in terms of the generation the speed, obviously like reducing the number of steps is really good, right? But as some kind of the advantages of the diffusion models, that what we have discussed in this class is that since we are having some kind of the iterative process in the generation, actually we could do some kind of the more some conditional generation or some guided generation. So we have seen lots of some kind of examples in terms of that. We are giving some kind of input in the denoising process. It can be some kind of like running some kind of backpropagation or some kind of doing some kind of the some manipulation with the output. So we are basically adding some injecting some of the inputs as some kind of guidance in the denoising process. In terms that we get some kind of some desired outputs that satisfy some kind of the constraints, right? So that is also kind of the power with diffusion models. Like while sacrificing the generation the speed, we can do some kind of add some kind of more the guidance in the generation the process. But if we basically run the one-step generation, it won't be possible to apply these techniques. So for some kind of the guided generation, with some kind of single-step generation, we might need to also consider some other kind of the options for that. So there can be some kind of the trade-off in terms of like reducing the number of steps. Any questions on this? So I strongly recommend you to basically check those out. And also the assignment 7 will be about implementing the flow matching. You can really try to basically like run some kind of reflow, basically changing the flow matching the multiple times and see whether you can really get some kind of the straighter the trajectories. So implementing the flow matching would be the last assignment. Course. So that's it for the wrap up on stuff.